So these are just some initial results for where we thought, okay, this is a good starting point because this is highly lipophilic. This is like a worst case scenario for solubility in water to try out this Buchwald-Hartwig reaction. And what is published, if you try this reaction in organic solvents, the temperature are in the range of 90 to 130 degrees. The time was 12 to 72 hours, and the yields are between 67 and 96%. This is actually what was published by Lipschitz, and we could also reproduce this. You can take the temperature down, if you do this in water, to 25 degrees Celsius. It takes 3 hours. The yield was really good. When we tried this with our own methodology with a cellulose derivative, actually we do this at room temperature. Initially, it took us 5 minutes, 95% isolated yield. If we heat it up to 50 degrees, it was actually done in 90 seconds, and the yield is even better. I mean, we have improved on this now, so this is something that I can disclose at this point, but I can say that we are generally better now than this. So we have different amines. I mean, we have tried ureas, everything that was published. We took a few examples actually to showcase that everything that is published so far with from Sachin and also from Bruce Lipschitz and from Novartis, that we can use with our surfactant, we can reproduce, but we are much faster. So that's, we're currently working on the publication actually. And yeah, most of the reactions are actually done within minutes and sometimes within seconds actually. So this is absolutely unprecedented, the speed that we can achieve for the Buchwald-Hartwig reaction. Of course, at that point, we were also wondering if that's only true for the Buchwald-Hartwig reactions or if that's also true for other reaction types. But also some other fundamental differences we noticed. So this is the Buchwald-Hartwig reaction in TPGS7 at 50 M. So at the setup, again, all the starting materials in here, then you start adding the solvent, TPGS water. After 5 minutes, that's what it's looked. After 2 hours is actually something that we observed sometimes, not always, but then it started clumping. And that would be a worst case scenario for process chemistry. I mean, Novartis has solved this problem by adding co-solvents, organic co-solvents, to avoid this clumping. But again, I mean, this at some point dissolved again, and then the reaction was finished. But this took like 3 hours. When we look at our surfactant, actually, we have a stable emulsion. So it's very different. So we never had this problem of clumping, actually. And actually, maybe it's on the next slide. Yeah, it is. So same reaction. This is TPGS in water, and this is our HPMC. This is when the reaction is stirred. This is the reactions once it's not stirred, and you can see the micelles stuff is pretty much going to the bottom, whereas HPMC is like a stable suspension. And that actually is why HPMC is used in the paint industry, because it allows the dyes to be evenly distributed in the paint. So that's another advantage or so, or how we differentiate actually from the micelle approach. This is an example that I can share with you doing the amide coupling. To me, is one of the most exciting results that we have right now. So this is for procainamide. So if you reduce this to the aniline, actually, then this is procainamide. The amide coupling, because the amide coupling is the most important reaction in pharma, actually. And if you do this in organic solvents, it takes 4 hours, 69% yield. This was done by Novartis and Professor Lipschitz, same time, 86%. And this was our first shot using these conditions here. We got down to 2 minutes, actually. And actually, we have improved this with the conditions we have now. The reactions are all done within 5 seconds. And to me, it's still unbelievable to me that it's so fast. It's so fast, actually, that we can't even measure the kinetics. So actually, we add the COMU at the very end.
So do you have a control experiment where you don't have coupling partner, or the EDCHOBD, and you just use your surfactant and then see?
And we have all the other control experiments, but I'm not sure if we. No, I don't think we have.
Because what we saw during the synthesis of TP5750, it spontaneously formed ester, which is more labile, and then.
Yeah, actually, that's a good point. That's one of the control experiments I have to admit that we didn't do. That's a good point.
Then actually you remove coupling
Right.
agent.
I mean, I have to say we are down now. Oops. To 0.1% of the surfactant actually, but it's a good, excellent point. It's a control experiment we should do, yeah, just to be sure that this. But actually, yeah, because when we add Komu, actually, we do it at the end of the sequence. So first we put all the other starting materials in, and Komu actually, the nice thing is once the reaction is done, it turns yellow actually. So, and when we added the Komu, immediately we saw the yellow color actually, and my postdoc immediately quenched the whole reaction and worked it up, and we got, we will almost have quantitative yields now. And the beauty about Komu is we don't need any chromatography, you just do a basic workup. That's because the Komu byproducts are water soluble. You get clean products without any column chromatography. And we do this within seconds. Again, it's to me it's quite mind-boggling, and it's, yeah, this has never been achieved for the most important reaction type in the whole industry. But there's room for actually working on the mechanism exactly, because of course I guess you're wondering now what is the cellulose derivative actually, and it's HPMC, so it's hydroxypropyl methylcellulose. So it comes from cellulose, which is the most abundant biopolymer. Also, actually the HPMC, when I actually ordered or tried to order the HPMC, I got it from a vendor and he gave it for free to me. He said, I'm not going to bother to write you that you have to pay for it. It's more complicated because it's so dirt cheap actually. So that's one of the advantages of HPMC. It's approved also as a food additive. Actually, in many of the sauces that you will buy in the supermarket, there's HPMC in there. In paint, there's HPMC. So it's in many different applications actually. And in the drug industry, we use it as an emulsifier. I mean, that's exactly where originally we thought, okay, this could make sense actually. We use it in PK studies when we do pharmacokinetic studies, when our initial drug molecules, when we submit them to animal testing. This is one of the helpers, how we can solubilize insoluble drugs. And you can fine-tune the properties by modifying the chain length actually, the methoxy concentration here, or here the isopropoxy group concentration. But you see actually you have a lot, which initially was quite surprising to me. I was concerned if you use HPMC with all these free hydroxyl groups around, that this will mess up like when we do the sulfonylations. Because there are so many hydroxy groups here, they could easily be sulfonylated, but it doesn't happen. Because I guess these free hydroxy groups are embedded in the water. And what you see here is that's probably a realistic picture how HPMC, the polymer, looks in water. It forms three-dimensional structures where there are lipophilic pockets, and that's probably where the starting materials are being dissolved, and that's where probably the reactions are happening. It's just a hypothesis, but that's the best we can do right now with our mechanistic understanding. But that's why I'm here, and that's why I want to collaborate with Sachin, is exactly to really work on what's going on. So we will work with dyes, and we had long discussions how we are going to approach what's going on actually. But again, conceptually it's very different, because you can actually also use this hydroxy group. You can put this on solid support. You cannot do this with a micelle, because the micelle is derived of a single molecule. So I think conceptually also this is really different and has a number of potential further advantages. And I'm sure actually that if I work with my colleagues now, I mean, usually in formulation sciences you use two surfactants. That's usually what you do. So I think this is just the tip of the iceberg if we learn from our colleagues in formulation sciences and apply this to chemistry problems. That's why sometimes we ran into solubility issues, even with applying our methodology, but I'm quite confident actually that we can overcome this in general. But we use actually the efficiency of nature, and I think that's, to me, is the take-home message actually. So we unleash actually the power of chemistry in water by using this surfactant. And these are from our patent application actually, so that was one fun part actually. Initially I was so happy that all these different reaction types actually work. Actually it took us some time to realize how fast these reactions are. Because I would have never in a million years expected that, I mean I was happy if they were done after an hour or so, if we were a little better than what was published actually. And now we realize, we look back actually at many of these reaction times and realize actually, I'm not sure if I should disclose this, but these sulfonylations are done in seconds. The ones that live into it. And operationally, again, we use only the minimum of the reagents. For the Buckfield Hartwig, we use one equivalent of the amine, one equivalent of the bromide, one equivalent of base, and that's it. So it's the absolute minimum that you need for the reaction to proceed, and the same is true for the amide coupling. And that's so cool, because if you look at the raw LCMS, it's just like one peak. And that's so fascinating, actually, and that's why. But that's, yeah, again, so we could show actually that everything that was published by Professor Lipschitz, by you guys here, by Sachin, and also by Novartis, we can actually do with our methodology. And also this multi-step, we tried it for one of our projects. It's a 4-step, 1-pot, where you just add reagents, actually. Actually, it was a Bock protection, then we did an alkylation, and then we did a Bock deprotection, and then did another reaction. So basically, it's you just add a little bit of your starting materials, and then you purify. It was 80% isolated yield at the end of that sequence. Yeah, so actually this is old, so we're definitely open to collaborate. the patent has been published. So, and in summary, again, I mean, this is state of the art what we are doing right now in the pharmaceutical industry. Basically, all the chemical reactions are done in organic solvents with all these caveats, actually, that the majority of the waste is related to using organic solvents. I should point out, we actually, in organic solvents, usually you have molarity of 0.1 is usually where we carry out our reactions. We do 3 molar reactions. So that basically brings down, if I have a 1,000-liter reactor with organic solvents, what we use in water is like 33 liters, just to give you an appreciation, actually. And actually, it sometimes even improves the kinetics if we even are more higher molarity. And again, this comes as a price. The organic solvents, they're expensive, toxic, and also they're regulated by legislation, and especially in Europe, this is a big problem. By 2022, it may well be that solvents like NMP, DMF will be banned, actually, to be used in Europe. And then we need to have alternatives. That's why Novartis is definitely at the forefront of this effort for this chemistry in water, actually. So to me, this is the landmark, really, where this whole field is taking off, actually, because what Sachin and Bruce have shown, and also Novartis, actually, with his vitamin E-derived surfactants, actually, that you can make chemistry eco-friendly, and that you can do this on a 100-kilogram scale, and that it's faster, cheaper, and more efficient than organic solvents. And with our technology, we hope to contribute and also further evolve the field. So I'm hoping that our data will generate a lot of interest because this is, to me, just the tip of the iceberg. And again, if you think about nature, the efficiency of nature is unparalleled. And if we can be a little bit more like nature, we will really transform the whole chemical industry. Okay, this is just a summary of what you've seen before. Again, this is also a pledge, actually, for academics to join the field, because the rules for chemistry in water are not known yet. So I think empirically we learned from Buckfield-Hartwig what is important for the Buckfield-Hartwig reactions, what kind of phases you need, what's the property of the phosphine ligand, is it bidentate, monodentate, for what kind. And I think we need to derive these rules for chemistry in water, because here, for example, for the Buckfield-Hartwig, it's TBUX-phos actually is the best ligand so far. But it's just, we need more screening actually to understand what are the critical parameters, and also what's the mechanism actually. So that's actually sort of the closing statement is there's great potential, unprecedented results actually. It's just that we need to get a better understanding of what's going on. Actually, this is a cool quote from Paul Anastas, who is the godfather of the 12 Principles of Green Chemistry. I had the pleasure to meet him actually at this UPAC conference in Venice 3 years ago. And I like this so much actually that I always put this in my presentation, because he said there is no desire to do the best green chemistry. We will do the best chemistry and it will happen to be green. And actually at that point I thought, okay, that's a really bold statement. It's like a vision. And actually with our data, now I'm convinced actually this is actually true. Because now that we can do amide couplings in seconds, that's unprecedented. It just shows what this chemistry is capable of. And with that actually, I would like to acknowledge my co-workers actually. So it was actually Johannes. He was the first postdoc on this project, and then Desi, who just left recently. I had 2 postdocs on this program, and my 2 associates actually, and that pretty much, these 4 people did all the work actually. And in parallel, we did actually all the drug discovery. So I spent, I mean, the postdocs were full-time on the project, but all the other people did like 5% at most. So I think I'm still amazed actually how much progress we made with so few people actually. That's the beauty of doing chemistry in water probably. And also again, thanking my colleagues in formulation sciences, because I think key again is that you leave your comfort area actually and talk to people outside your area. I think that's where real innovation is happening. And that's why I appreciate all the discussions I had with you guys already, because I think innovation is happening once you leave your comfort zone, talk to people, get inspired what other people are doing. And again, yeah, Professor Lifshitz, I mean, for this thought-provoking work. And yeah, if you want to work in the best places to work in Europe, then you should be considering working for AbbVie in Ludwigshafen. And of course I want to congratulate, because this is actually, without the work from Bruce Lipschitz and Sachin Handa, we wouldn't have been in this area. We wouldn't have been able to contribute. So I'm very grateful, and I was also very happy that I was the organizer of the symposium where actually Sachin got recognized. So again, congratulations also on behalf of my company actually. Keep the good work going. And with that, I'm done, and thank you for your kind attention.
Questions?
So you said it was a stable emulsion, so a couple of questions about that. One, is it an aggregate? I mean, is there anything known about the supramolecular structure or the molecular structure? Does it have to be a helix? The rest, and then how do you break the emulsion and get your products out?
Yeah, okay, good question. No clue about the first, because we didn't have time to look into this. I mean, I'm looking more into the application, so I cannot say that's exactly why we need this collaborations with you guys.
I thought maybe the structure was known by all the paint chemists.
Yeah,
right?
yeah, but I mean, it depends also if we add a base, we see differences. Sometimes actually we get a clear solution then. So you influence also the structure of the surfactant by adding the reagents. So that's why I think there will be no global answer to the question. It needs to be investigated case by case, and also to learn from that actually. Because sometimes if we add, I mean, it may well be that organic bases are definitely altering the properties. Second question, what was it again?
How do you break the emulsion?
Oh yeah, okay. Actually,
your product?
it's super easy now. Actually, we can clean up wastewater. That's what we noticed. So if you add sodium sulfate, saturated solution, you crash out the HPMC, and then you can filter it off. It's really easy. You can use any from the Hoffman ionic strength. So you can use phosphates, for example. It's very easy to crash out HPMC, filter it off, and then initially when we used 2% actually of the HPMC solution, we had sometimes our product trapped in the HPMC, because HPMC is so good at retaining these, with the lipophilic pockets, organic substrates actually. And we also measured actually the palladium content of the HPMC, and most of the palladium is actually trapped when we crash it out, as almost exclusively in the crashed out HPMC. And then you can just filter it off, and we just actually then analyzed the water phase, and there were just the salts in there. The potassium bromide and the sodium sulfate, and nothing else, no other organic components. So actually that's why we were thinking maybe we should use this process when it's contaminated with mercury or so. That would be one way to clean up wastewater. I mean, that's something I still have on the back of my mind. But there's many unknowns, but that's why I'm here. For us in industry, it's important to apply this to our problems. And again, to me, the striking advantage is also that we can do reactions that we couldn't do before. I mean, that's the value for us. But to improve this, we rely on you guys actually to help us out to work on the mechanism so that we can further improve this process. Yes?
So the water you're using for these reactions, is it DI water, tap water?
It's DI water actually, just for consistency. You can use in principle tap water. We noticed the bench stability is different because at some point we had some algae growing inside the water actually. So that's why we use this highly purified water, because we have sometimes water of the surfactant solution standing around for years actually. So that's the only reason, but in principle, you can do the same reactions using tap water. Actually, I'm collecting samples actually from different places where I'm going actually because of the salt content to see how that has an influence. I also would like to do a study where you use red wine, tea actually, like Phil Barron did actually, to show how selective the processes are. But that's definitely would be a fun publication to investigate that.
You said that the HPMC and like the palladium and all that crash out. How recyclable is that?
That's a good question. We have not recycled in Medchem, I don't care at this point. But in the future we'll use membranes actually. We'll not even crash it out, but we use membranes actually for the separation of the water phase and the organic phase. So we haven't done that yet, but I'm sure that because I'm convinced that the palladium sticks to the HPMC, that is very recyclable. So, but that needs to be shown. Maybe Sachin, once we start our collaboration, can do the recycling study.
They published patent last year, and I submitted proposal to IUPAC.
Mm-hmm.
And then I got a comment back. I missed your patent. Somehow they know.
Right. Yeah, because I was at the conference actually.
It was not even published.
Yeah.
They said it's already with some pharmaceutical industry concept we cannot fund. So
Oh, I'm sorry, I didn't know that actually.
I think it was same cellulose based chemistry. In my very first year I submitted
Right.
by the IUPAC. I think probably Paul Nestus was a member.
Right, yeah.
He must knew.
Yeah.
They didn't fund, but otherwise you have been scooped by this time.
Yeah, exactly. So
One more question from my side. Maybe it looks odd to you guys. I'll come back to you. Did you try Grignard formation in water? Maybe it looks, as I said, as a traditional organic chemist, you think it's a very stupid question. You cannot form Grignard reagent in water. Did you try it?
No, but there's Capriati. He has shown that you can do actually these Grignard reactions in water in seconds again. So that's why I think the proof of concept is there. We haven't tried it. Actually, at some point we were so bold that actually my postdoc, but that didn't work actually. She just put in the Grignard reaction. That was an early day bold experiment. But in principle, I think since Capriati has shown that you can do it in water, I'm sure that you can do it with the surfactant water too, if you follow
That
that.
must be in situ generation of the Grignard, right?
No, actually, it's with the stirring. So the hypothesis is that the organic materials at the surface of the water, and that's when you add the Grignard reagent, it reacts at the surface of water. That's why for the Capriati procedure, the stirring is really important, so that the organic material is on the top of the surface, and that before it gets quenched by water, that the reaction is being happens. That's at least in the paper from Capriati, the explanation. But I mean, also like the Negishi couplings, actually, it was shown that you can actually form the in situ, the zinc organule, and then have the coupling by a Dutch group actually. The yields were not that super fantastic. That's why definitely I would recommend to use the surfactant approach. But in principle, you can form actually, because it's faster, the organule and then the palladium and then the coupling before it gets quenched actually, which I again thought is so counterintuitive, because when I did a Negishi coupling back in the days, I was always making sure that there was no water around.
I mean, I just back to your question. Most of audience doesn't know why micellar catalysis work. What are the conditions you need to use? What are the precautions? These are not precautions. I mean, you have to be more cautious because rules are different, as you mentioned. And actually, we submitted in the form of a review of, you can say, chapter to Wiley. So, I mean, I will be happy if you can share with the industry, like they follow these rules, and they will not have any problem of not only reproducing, but to come up with new chemistry.
Right. Yeah, I think that's exactly what is needed, is actually to expand the scope. Because we investigated 21 reaction types, different ones, and of course, many of them are really important to us, others are less important, but really to get an understanding of scopes and limitations, it would be good.
Rene, you have a question?
No, you just addressed, I was curious about the Negishi in water, what was going on there. You just addressed that with Grignard and stuff like that.
So, any other question? So, what do you think the scope of this chemistry with the HPMC?
I think to me it's the tip of the iceberg. I mean, this is just a starting point to me, but what we got, the results are unprecedented. I think, to me, chemistry in water is the future, actually.
Yeah, because as academician, we want to not only see like what you get, but how chemistry works, why it works.
Right. But I think,
That's the main
to me, the key learning experience is really, we should look how nature is doing chemistry. I mean, like photoredox chemistry in nature is, you have to look to a tree, actually, and get an appreciation how efficient photoredox chemistry is done in nature, actually. So I think we are still, like amateurs compared to how nature is doing chemistry.
Okay, so the last thing I think for students who are in organic synthesis, make sure before you publish anything, ask your colleagues, what you discovered is reproducible, as we
Right, yeah.
mentioned, okay? You publish something, it's not reproducible, let's say, I can share one experience, I want to make one product in graduate school. I followed paper, I will not tell you which paper, who is the author, okay? I spent 3 months, I was not able to get that product, and I was in trouble in my PhD.
Yeah.
And then, 2 more postdocs tried, didn't work, okay? So, you publish something, it's not you made data or something, maybe you missed something which is very crucial to report it, but you can put other students' life in danger, one. Second thing is you will be wasting time of the people from industry if they are not reproducing your chemistry, okay? So don't rush to just publish, make sure it must be reproducible. Ask your colleagues, can you repeat one of my experiment if it is reproducible or not, before you give to your boss for publication.
Yeah, that's a really important point. Also, it kills the patent application, because if somebody is challenging your patent application, somebody independent has to reproduce exactly from what you have described in the patent application. And if that's not reproducible, the patent is gone. That's why it's a very important point.
Your reputation will be gone also.
Yeah.
It's not your, but the people associated with you, it will be gone. Okay? So, well, in the last, we want to appreciate you with the
Thank you.
award.
Oh, thank you very much. We'll get a special place in my office. Yeah, thank you so much. That's cool.